Okay, so from yesterday. Okay. For those of you who were not here, there's certainly material that you can watch. That is your responsibility to do so. Okay? So for the rest of you who were here, or even if you were not, okay, give me a positive ion. Okay? What type of iron? It's not possible. Not +1.
+4? +3.
Not +4.
+3.
Okay.
+3, +6, +2.
Okay, so you want 2 or 3?
2.
Okay. So then give me an example of a halogen.
Chlorine.
Okay. So you said iron is +2. So we need to finish writing that compound.
2 chlorine.
Okay. So by now, is it fair to presume that we all know that why there's a 2 there? Is it, you've got to say something if you don't understand why there is a 2 here. Okay? So then let's go ahead and react that with, okay, maybe a metal that's possibly more active than that. We'll say aluminum. Okay? So everything on the left of that arrow is called a what? Is a reactant. Everything to the right of that arrow is going to be what?
Added chemical reaction.
The product then. Okay? So one of the things that will happen is you will be responsible. If we're going to do that, we're just going to sit outside.
Now put it.
Okay? So if we needed to complete this, if it was called a single replacement reaction, that means this aluminum is going to replace that iron, but it's on this side. So that means we've got this, and then now the iron is neutral. Okay? But we need to finish that aluminum chloride on the product side. Yes?
How would you know that aluminum and chloride go together?
Because I told you. Until this point, I'm telling you that it does.
Okay.
You will learn that they will switch, but you haven't learned that yet. Okay? So we still have to do some work on the right hand or product side yet. Does anyone know what that might be? Yes?
We gotta
Do you add a chlorine? Do you add a 2 to the iron? Or no?
Nope. We said the iron's neutral now.
We need to put a 2 in front of the aluminum on both sides.
Okay? So it's fair to say we can go ahead and put our elements down in the. Okay. So what elements do we see besides iron?
Chlorine.
Chlorine and
Aluminum.
Okay. So iron's left.
You got 1.
Iron's right.
1.
Chlorine's left.
2.
Chlorine's right.
1.
Aluminum's left.
1.
Okay. Aluminum's right.
1.
So I'm just going to extrapolate this. I'm going to say at 3 minutes and we'll say 30 seconds. Okay? Now let's go ahead and try to balance this.
Put a 2 in front of the
Chlorine.
Put a 2 where?
in front of the aluminum on the left side.
Okay.
And right.
So that changed this to a 2 and that to a 2. Okay? And then,
That's a 2.
okay?
No, just kidding.
Now we're stable.
Okay? So we are about a minute into it because I said I'm going to extrapolate that at 3 minutes, 30 seconds. It's now at 4:42.
I'm going to write this down.
Okay? How many believe that's right? It's balanced.
Are we trying?
But there's something
Are we trying to balance it?
something's alone and it needs a 2 or something
Nope.
like that.
No, we don't have any diatomic molecules. Okay, how many think are wrong then? Okay, well, we are a little bit over, okay, almost 2 minutes into this. Okay, one of the things we can do, what's the charge of the chloride ion?
What?
And you got 2 of them, so then it was predetermined. You said this iron had a what charge? +2. Okay. Aluminum by itself, so it's stable. Iron is by itself, so it's stable. Okay. The charges will not change when you go to the product side. What is the charge of chlorine? What's the charge of aluminum?
No. +3.
Does that add up to 0?
No.
Okay. So what has to happen then? Okay. So we're still not done yet. We are almost 3 minutes into this. And those 3 minutes,
You gotta put a 3.
those 3 minutes, you were 100% wrong. Okay? And those, I don't know if you want to call them mistakes, but, okay, a way that we can make sense of this, if you were a basketball fan, and if you follow SDSU men's, the women play today at 1. What about the SDSU men?
They lost last time.
They lost. And when it comes to mistakes, let's call it that maybe missed opportunities, we could say are mistakes, it happens. Those only get magnified in the postseason. During the regular season, you try to learn from them, okay? So this is kind of like our regular season here, this mistake that we made. Once you get into the postseason where you're getting into evaluations, those mistakes only get magnified. And especially for those of you who take general chemistry in a couple of years, those mistakes only get magnified, okay? Because like I said, we had spent 3 minutes on this equation, which is fine, but it's just that even everything after that still would have been 100% wrong. We're not trying to say, oh my gosh, you people, you really need to focus in on this, okay? No, that's not what we're saying. It's possible that you make mistakes. So if these are made, what do we say about mistakes? 1, try to learn from them, and 2, try not to repeat them. Okay, so now we can go ahead and perhaps start over, okay, because we know that that's wrong. I mean, the chances of that being correct are very minute, okay? So let's go ahead and start over with these. So now, chlorine's right. Aluminum's left. Aluminum's right. Okay. So, yes.
Should we balance them before we do this?
Mm-hmm. When we say balance them, that means you balance the compound over here. Okay. So here you can look at least common multiple again. These are even, your chlorides. These are odd. These come in pairs. So you need to get that chlorine up to an even number. So how would you go about doing that?
6.
Okay. So if we double this, okay, that gets distributed through the entire compound, okay? What is 2 times 1?
2.
What is 2 times 3? Okay? So then what has to happen on our left side now? We've got 2 aluminums on the right and only 1 on the left, so what do we need?
2 in front of them.
Okay, put a 2 there. And now our chlorides still are not balanced. We've got 6 and 2.
3 in front of our iron.
Okay, so if we put a 3 here and distribute that through the entire compound, what's 3 times 1?
3.
Okay, and what's 3 times 2? And then now we've got 3 to 1. Okay? So notice if we had 4 blanks, what would we be writing in those 4 blanks?
3, 2, 2.
Looks like 3, 2, 2, 3. Okay? Make sense?
Yes.
Funny chemical reaction, right?
Very fun.
Okay. So let's go ahead and pick up where we left off. And some intriguing questions that some of you may, well, I shouldn't say may, you did ask is, how do you know how many valence electrons these elements have? And other than just me telling you, that's what it does, because that's what the periodic table tells you. But how did early chemists know that? Well, that is a good question. That I don't have an answer for, okay? But the importance of something like that is just the idea of being able to synthesize, you could say, our own, whether it's medicines, that's probably the important part, is this content continually builds upon itself, whether it is general or inorganic chemistry to what we see as organic chemistry. Okay, so we had this equation, that's where we left off, and did we talk about this yesterday? Okay. Yes. Okay, so hang on. Okay. The idea behind this is it was a sealed container, okay? Because what happens is when you take this red substance or mercuric oxide. Now, the reason we say this here, mercury 2 oxide, is it's much easier saying that than mercuric oxide. If you say that, you don't need this Roman numeral 2. Or if you say mercurous oxide, then you don't need the Roman numerals. You're using the Latin terms to explain that. But it just makes it much easier if you use the Roman numerals, okay? You say the same thing for ferrous and ferric, Nicholas and, is it nickelite maybe? I'm not quite sure. But when we change the names of those positive ions, you're removing the need for those Roman numerals. But I think you'd agree that at your level, it's not until you maybe take this in college, you would have to know those names. Cuprous being +1, cupric meaning +2, okay? There's no reason that you should have to know that at this level. Okay, so like I said, what had happened is a closed container is the key. Because what happens is, what causes a chemical change, or what causes a chemical reaction? Heat is one. Light can do it. A catalyst can cause a chemical reaction. Oxygen, if you oxidize something, yes, that can cause a chemical reaction. Hydrogen can if things get reduced. Okay? So upon heating this, into a silvery liquid. So what happens is breaking that apart in what we call a decomposition reaction. And that phone making that sound almost really startled me. I don't know whose phone that was, but since I'm standing in the back of the room right in front of the wood demon here, well, yeah. It's a demon because it holds your cell phones, right? So luckily we don't start shaking because we're not on our technology. Okay? And I'm not smart enough. I did not give it its name. Just like Jerry the Owl back here, students named this. This was also given the name as the Wood Demon.
Where'd you get Jerry from?
Mrs. Kesenbeck, when she was here, donated it to the library. Librarian left, so then, or no. It was donated to Mrs. Kesenbeck, Mrs. Levon Kesenbeck, if that makes sense. She retired. She was going to give it to the library. They didn't want to put it up in the library, so thank you to Mr. Rick, who said, "Do you want this?" I said, "Sure." I didn't know of a good place to put it, but I thought, well, another pair of eyes in here. How about right above the door? Okay.
You talking about Rick Bell?
I am.
My grandpa.
Okay, Grandpa Rick. Okay, so then what had happened is, since this container was sealed, he could measure both products. You could get an actual measurement of the gas in this test tube. And in this case, this gas was what?
Muriatic acid.
No,
The red powder.
Mercurial.
no. You're going to hit yourself over the head because we did this yesterday. We just did not apply this terminology. What was the gas that was in this compound? Someone probably said it and said, "I said that already." No. Oxygen. Okay?
I said that already.
So then, yeah, we got to play along. Of course, someone has to put their 2 cents in. Okay. So this was probably the basis for what we consider modern chemistry. Why is something like this important? Well, we're always looking for innovative ways. Yes.
Oh, I was going to say, why? Because your professor or whatever it is.
Well, that was just balancing the chemical reactions. But in this case, this contribution here, okay, understanding these chemical equations, okay, it's a way for scientists to improve upon maybe existing substances, whether it's a more efficient way to make that concrete. Well, not concrete. Yes, concrete. Because that's a chemical reaction that water dehydrates with the water, sand, gravel, and cement. The cement is the major catalyst that causes water to dehydrate, and there it goes from cement to concrete. Okay? That's why some of you farmers might say, we are going to go pour cement. You can pour cement, you can't pour concrete. Why not?
Concrete's the hard stuff.
Yes, concrete is what you walk on. Well, you can walk on cement too, but you're probably going to fall into it or dip into it or sink into it. Sure. And one of the things that if I was you sitting in that position, you got to be thinking to yourself, we've got so much modern technology, why would we ever write this content out? Well, one, it's a way of documenting what you've done, and two, is a way that you can repeat that then. Because one of the commercials that SDSU has is they show students working in a lab, and in the background you see a whole bunch of organic compounds in the background, and they're trying to do different types of experiments, maybe to improve upon a type of product. Maybe it's as simple as making a different type of dye. Okay, not that this is an example that we give in general chemistry, but there's a powder in here that after a chemical reaction it turns brown. And some people, when we say brown, kind of like that of chocolate. Some people maybe like the color brown, a chocolate color. Is chocolate brown or black?
Either
Brown.
one.
They can
It depends
Well,
on
Okay.
the chocolate's black. and
Okay,
then-
so we're going to say it's brown. Okay, so some people again may choose to have that type of a color. So this type of additive or chemical reaction might be a way to make a better type of paste or ingredient for making the color brown. Okay, so that is an example of what we're trying to illustrate here, that understanding this allows you to try to make improvements upon existing materials. Okay, and you could maybe even, what's an alloy?
Oh,
A
like
combination of metals?
It's a combination of metals. So what that would mean is if you can improve upon different types of alloys like what you would mix with aluminum, probably, I don't know how accurate this is, but the most common place for aluminum in transportation might be what?
Hey.
No, transportation,
Oh.
not cars.
Semi.
Airplanes.
I guess
Okay?
that.
So maybe it's different types of alloys that you can use to make not only planes stronger, but also lighter. Okay? So you might say, well, if it's going to make it lighter, is that going to make it less durable? Of course, the answer is no. Because one of the things to think about is if you have maybe a very nice vintage muscle car, maybe it's a Dodge Charger, maybe it's a Chevelle, maybe it's a Mustang. One of the things you might say, I am not going to drive it in the wintertime for 2 reasons. One, you might get into an accident, and 2, it's going to rust if you expose it to the elements. So maybe you want to wait until maybe May or June when chemicals have been far washed off the road. So there's no more salt on there, because if that gets onto your chassis, which is your underbelly of your vehicle, or onto the paint itself, it can actually cause that to start to break down, deteriorate, and as you said, rust. Okay, let's just get through this equation here. So as nickel 2 chloride is added, okay, to sodium hydroxide, new products are formed. Okay, so what we want to illustrate then, for those of you who wrote that down, okay, how would we write this equation out? Okay, it said nickel chloride, right? But what type of nickel? Okay, so go by your negative charges. Nickel has chlorine has a charge of negative what? And what's the charge of that nickel? Okay, so how many chlorines do we need?
2.
Okay, so if this is added to sodium hydroxide, what is the formula for sodium hydroxide? Not S, that's sulfur.
Where is sodium at?
Element 11.
Na.
Okay,
Na.
okay, what's the charge of the hydroxide ion?
-1.
What's the charge of sodium?
Probably a
+1.
Okay, so what we are doing here from our reactant side, okay, switch the positive ions with the negative ions. This would be a double replacement reaction. So if nickel has a positive charge in this compound here, it's going to bond to the negative charge of this compound, but on this side. So what does that tell you? Nickel is positive over here. What is negative in this compound that it can bond to, but on this side of the equation? Hydroxide. Okay? Then what can sodium bond to from this carbon, but with a negative charge from this compound, but on this side of the equation?
Chlorine by itself.
Okay? Because whoever said that, they said it backwards. That's what threw me off. Always write your positive ions first. So NaCl, or sodium chloride. Okay. So, is that written correctly so far?
No, you need to stabilize.
Okay. Now we need to stabilize something on the right-hand side. The charges do not change. So something is incorrect on that right side.
2 OHs.
Yeah.
Or 2,
Okay.
And then that makes 2 nickels.
Okay? So that means that hydroxide's still -1, nickel's +2, this is +1, that's -1, so that adds up to 0. but this does not add up to 0. How many hydroxide ions do we have right now? 1. But how many hydroxide ions do we need?
2.
We need 2 of them. So be careful on how you say 2 hydroxide ions. You have to put this in parentheses. Okay, now it is written correctly, and we can proceed. Yes?
Now do we put a 2 in front of the Na and OH, which would change the rest of the column, or can we just put a 2 next to OH and
OY.
Okay, we'll get to that. Okay? Not a bad question. How many of you feel comfortable? I would still suggest that you do this. What are some elements that we see on each side?
Nickel,
Sodium,
chlorine.
nickel, chlorine, and hydroxide.
Now, that brings up a good point. You can do this, but since you see a hydroxide on each side, you can also keep that together, which means this. Keep the OHs together. Key important question. Does that make sense to you?
You can split them.
You can split it up, or you can keep it together.
Why would
Well-
you want to split it up?
Sometimes you have to. Because if you don't have a hydroxide on this side, well, then you have to split them up. Okay? It doesn't happen all the time, but it can. And an example of something like that would be, let's say, as far as photosynthesis is concerned. What do you know about photosynthesis? It's carbon dioxide is what plants take in. What else?
They produce oxygen.
Okay? So they take in water, and then they produce glucose. And then, well, that's what jumpstarts this reaction. Okay? So an example of this, you could say you've got hydrogen hydroxide. That's still H2O, isn't it? So still 2 hydrogens and 1 oxygen, right? Okay? So you could write that as HOH. But do you have an OH compound on this side? No, you do not. So sometimes you have to split them up. Okay? But in this case, you can keep them together. So does that confuse anybody when we say keep them together or split them apart? Because now is an important question to ask yourself. Front row, do we understand this? Because if you are nodding your head yes, and you really do not, you are not helping yourself. Front row. Second row.
Down.
Absorbing it like a sponge, okay? Third row. Okay. So for those of you who said no, what do you feel more comfortable with? Splitting these apart or keeping them together?
Keeping them together. 'Cause
I'm going to do it both ways, but I just want to know which one we should do first. Keep them together. Yes.
I feel like if we had to split them apart, like in the parentheses, I feel like you'd have a 2 or something behind
Okay. So let's go ahead and write this out. Nickels, left. Nickels, right.
2, but yeah.
Sodium's left.
1.
Sodium's right.
1.
This is probably what you're getting at. Chlorine. Okay? Hydroxide's left.
1.
Hydroxide's right.
2.
Okay? Chloride's left.
2.
Chloride's right.
1.
Okay? And then we're going to do both of these at the same time. How many oxygens are on the left side? How many oxygens are on the right side?
2.
How many hydrogens are on the left?
1.
How many hydrogens over here?
2.
Okay? So, it looks to me like there's only one place to start, and that's with your chlorines, because you have 2 on the left side and only 1 over here. So a lot of this is just trial and error. It's not that you need to know the answer right away, because sometimes it's just not going to be that, let's say, obvious. So if we want to get 2 chlorines on our product side, how do we get 2 over here? You don't do this in the middle of the compound. Don't put a 2 here.
Put a 2 in front of the NA.
You have to put everything in front because otherwise you are changing the formula. Yes?
OH2 the same thing as H2O?
No. Because if you distribute that, what's 2 times 1?
2. What?
What's 2 times 1?
2. Oh.
What's 2 times 1?
That's probably 2.
That's not H2O.
That's H2O2.
That's peroxide. Yes.
Okay, so put the 2 in front of NA.
Okay, so let's go ahead and do that.
You do that. They had to put the 2 in front of the other NA on the left side. Right?
Well, let's not put a 2 here and not finish this first, okay? What's 2 times 1 for sodiums? Okay? What is 2 times 1 for chlorines? Okay? So now, notice whether you're looking at your hydroxides or your hydrogen and oxygen. Do we need to increase this side or this side? Okay? So here's a clue that would tell you that. So if we put a 2 here for sodiums, 2 times 1. For oxygens, 2 times 1. Hydrogens, 2 times 1. Okay? Or if you kept them together with your hydroxides, 2 times 1 hydroxide gives you what? So what does that look like to you?
Stable.
It's balanced. You can keep them together as hydroxide, or you can split them apart. So what are your 4 numbers? 1, 2, 1, and 2. Now, when I put this in the box, does anyone not understand where these numbers are coming from? Front row, do we understand where they are coming from?
I get them all except the 1.
Okay? Second row.
The first one.
Second row.
Probably.
Oh, never mind. I get it now.
Yeah.
Sorry, Tom.
Okay? Third row. Okay, so what had happened in front of each one of these, okay, before we even started, there are 1s in front of these. Okay, so each one of these, there's a 1. Okay, nothing has changed. Everything times 1 gives you what? Gives you the same number back. Okay. So what had happened is when we said there are 2 chlorines on our left side and only 1 over here, we changed that to a 2. We distribute that through the entire compound. So this 2 is being represented by that 2. That's where we get that answer from. Okay? Then once we had done that, we had 2 sodiums over there and only 1 over here. So what did we put in front of here? We changed that 1 to a 2. And that's why that number 2 is there. These blanks are the same ones that we see in front of here. It just makes it easier to compile all those answers together. It just makes it easier to read this rather than reading an entire equation where you see all that content, okay? Because otherwise you start to cross your eyes and it gives me a headache and get confused and just makes things easier when we see this. Okay, so I'm going to hit pause here for just a moment. Let me hand out your paper here. I have not formally assigned the vocabulary yet, but what I want you to do on this paper, all of these lines over here is just like what we're illustrating here. They're all 1s right now, okay? I wouldn't put anything in these blanks yet, but you can perceive that they are all 1s in front of each one of these. So on this front side, go ahead and pick 1, 2, 3, 4, or 5.
4.
Okay, number 4, okay? Says as follows. Looks to me like we got cobalt iodide, but what cobalt? positive what? Positive 3. And then we've got what type of nitrate? Or excuse me, nickel. Must be plus 2, correct? The reason that's important is because that's why there's a 2 here and a 3 over there, because this cobalt was plus 3, minus 1, plus 2, minus 1. So these charges do not change. So you are applying everything that we've learned so far.
So the charges have already been, like, exhausted
Yes, you don't have to balance anything out yet.
on everything.
On this paper, everything. It's when you have to complete a reaction is when that gets to be a little more important. So one of the things that we can do, we're running, do you want us to work through it, or we give you the answer and you figure it out why you got that? You sure you don't want the answer?
Yes.
I think the answer would be fine. but
Oh,
I think I'm sorry.
okay.
Hey, there are more people than you.
My opinion, okay? Stop right
Okay,
Your opinion doesn't matter.
because that got you into trouble last time.
there.
Okay, so to help ourselves out, what elements do we see besides cobalt? Nickel, iodine, and do you want nitrogen and oxygen or NO3?
Nitrogen and oxygen.
Okay, all right. Okay, but some people probably prefer to keep them together because it works. Cobalt's left,
3. No, you got 1.
cobalt's right.
2, 1.
Nickel's left. Nickel's right. Iodine's left.
3.
Iodine's right.
2.
Nitrate's left. Nitrate's left.
2.
Nitrate's left.
6.
Nitrate's left.
2.
Nitrate's right.
2. Oh,
Okay.
Oh, there's 3 oxygens. Oh.
Wait, right? Right, it would be 6, wouldn't it?
This is a 3. This is a 3, isn't it? Okay. So the cobalt's, or excuse me, the nitrate's left is correct, but the nitrate's right is not 2,
It's 3.
it's 3. Okay? And then nitrogen's left.
6. 2.
Is it 6 or 2?
2.
Okay? Nitrogen's right. Oxygen's left.
6.
Oxygen's right.
9.
Okay? And I guarantee, trust me, this works out a lot easier, but you can split them up if you want. So where do you think is the best place to start?
Nickel.
Iodine or here? Oh, well, nickel's already balanced. Okay? So to the right, you see that there's 4 blanks. There's 1s in front of these blanks right now, correct? Okay. So if we're going to start with our iodines, that's fine. We've got 2 iodines here and 3 over here. You need to get this up to an even number. Okay? By 2 or 6? Okay?
Has to be multiplied by 2.
Okay. So then how many cobalts do we have now? Okay? And then how many iodines is that?
6.
Okay? Now, let's look at our iodines now since we started there. We've got 2 over here, but we need to get that up to a 6.
Put a 3 in front of the.
Put a 3 in front of here. How many nickels is that now? 3. How many iodines is that?
6.
Okay? So now you can look at your cobalt next. We've got 2 on the left and only 1 on the right. So what would we put here?
2.
Okay? For cobalts, that's now a 2. And then how many nitrates is that?
That's gonna be
2 times 3 is what?
6.
Okay? So nitrogens. 2 times 1 times 3. Okay? Oops, I did that on the wrong side, didn't I? Okay, so this was a 6. Okay, so for oxygens, 2 times 3 times 3.
12. I
18. Okay? So now, let's go ahead and do our nickels now. We've got 3 on the right side and only 1 over here.
Times it by 3.
Times it by 3. How many nickels is that now? Okay. So how many nitrates is that now? 3 times 2?
3. 6.
Okay. So nitrogens, 3 times 1
3.
times 2.
6.
Oxygens, 3 times 3.
9.
9 times 2, 18. So we had all these 1s over here. Is this still a 1? Now a 2.
3.
This was a 1. It's now what?
3.
Okay. This was a 3 over there, or excuse me, a 1, but now we put what?
3.
And this was a 1, but we changed it to what?
2.
Okay.
Yes,
If you are having problems with this, I highly, highly suggest that you find someone to help you, because it is not going to get any better. Find an upperclassman, because they said, oh, balancing chemical reactions. I can help with that. You just have to ask. That's all. We'll catch up to you next time.